Okay, so we will begin by treating the derivative as a function. We just saw in our last lecture how it can be defined at a given point. But if you can define it at every point, and which is possible with all functions, all nice functions we're working with, then why not consider it as a function? And the question is, can we find the derivative of a function as a function by using the formula that we gave last time? And how would we use that formula? We would just need not to specify the point that we're finding the derivative at. So in other words, here's how I would start. I would just say that the derivative of a function at a point x is simply the limit as h tends to 0 of f of x plus h minus f of x divided by h. And if you look closely, you will realize that this is exactly the formula that we used last time, with the difference that x was specified to be a number. In some sense, this is the case here. It's just that you never reveal what the number is. So you find a formula for the derivative at any number x. Let's do an example so as to see how this works. So our first example is to use the definition of the derivative in order to find the derivative of f of x equals x squared. Okay, that should be a nice example. So again, I start with our formula. And this will be the limit as h tends to 0 of x plus h whole square minus x squared divided by h. Now, as usual in these cases, and now it becomes a little more obvious when we work with a general function, we expand. And then, as we had mentioned before, and it's still true for this case, anything that doesn't have an h should go. And what are the two things that do not have h in them? This one and that one. They're gone. So now you can factor out an h on the top. So you will have h times 2x plus h over h. And let's write it in a clean way, 2x plus h. And let's understand that you see that you have two variables in this case. But in some sense, the variable that matters for this limit is h. And in order to compute this limit, we plug in h equals 0, and this gives us 2x. And of course, we just found something that we already knew from the formulas that we have provided, that the derivative of x squared is equal to 2x. Okay, so why don't we first do another polynomial? So use definition of derivative in order to find the derivative of f of x equals x cubed plus 2x. Let's see. So how do we solve this? We will have that f prime of x is the limit as h tends to 0 of f of x plus h minus f of x over h. So we just rewrite our definition. And this will be x plus h to the third power plus 2 times x plus h. And we subtract from it f of x, which is x cubed plus 2x. So we have a slightly more interesting quantity to work with. Now, let's expand everything on the top. And let's also get rid of all the parentheses. So we'll have x cubed plus 3x squared h. What I'm writing is really the formula that everybody should know about the third power of a sum, which is this. And then I just distribute the 2 in the second parenthesis. And then I just distribute the negative sign in the last parenthesis. And I divide by h. And now if I'm lucky, everything, I'm correct, everything that I told you about things that do not have h that should eliminate should materialize. So indeed, x cubed cancels with a negative x cubed, 2x cancels with a negative 2x. And from everything that remains, I can pull out an h from each term. So I will have a 3x squared here, plus 3xh, plus h squared, plus 2, divided by h. These two things cancel. Let's write it in a clean way once. So this will be 3x squared, oops, squared, not cube, 3x squared plus 3xh plus h squared plus 2. And when we plug in 0, we will get 3x squared plus 2. And we should have expected this result. Okay, let's keep these examples going. Let's do one more example where actually we don't know the answer in advance. So use the definition of derivative in order to compute the derivative of f of x equals square root of x. I mean, we don't know the answer to this question in advance. Let's see what is the derivative. That should be interesting. So as usual, we identify the derivative as the limit of this differential quotient. And what do we do in such cases? Multiply and divide by the conjugate quantity. And on the top, we're going to get something very nice. Namely the difference of the two squares. That is going to clear the square roots. So this will be the limit as h tends to 0 of x plus h minus x over so this will be the limit as h tends to 0 of h over h times square root of x plus h plus square root of x. Now the h's cancel each other. What remains on the top, of course, is the number 1. And now we can plug in. And please note that what we're doing is meaningful for x greater than 0. So what we find is 1 over square root of x plus 1 over square root of x the moment we plug in h equals 0, which is 1 over 2 square root of x. So we have a nice formula to remember from now on. The derivative of square root of x is 1 over 2 square root of x. Okay. Okay, why don't we find one more nice formula? So do the same. So use the definition in order to find the derivative for f of x is equal to 1 over x. Okay, so let's do this. Again, I'm going to work the same way. And you will see that actually the work I'm doing looks very much like the work that we did for individual points. Algebraically, it's not such a bigger challenge. So the derivative will be the limit as h tends to 0 of f of x plus h minus f of x over h. And this will be the limit as h tends to 0 of 1 over x plus h minus 1 over x. And here I need a big denominator. The whole thing is sitting over h. So clear the denominators on the top so that we have the same denominator. So multiply and divide by the denominator of the other fraction, x over x plus h times x minus 1 over, not 1, I need to multiply and divide by x plus h. And on the bottom, I will have x plus h times x. And the whole thing is sitting over a denominator h. So this is the limit as h tends to 0. And I have x minus x plus h over x plus h times x divided by h. And let's make this into a simple fraction. So on the top, I will have just x minus h, and the bottom will be x plus h times x times h. And here we will have a very pleasant cancellation. So I have a minus h, x plus h times x times h. This cancels with that, and this gives us limit as h tends to 0 of -1 over x plus h times x. Time to replace h with 0, and this will give us -1 over x times x, meaning -1 over x squared. So we get another formula which is worth remembering and we didn't know before. Okay, actually we will realize that everything is part of an umbrella formula that we're going to discuss in the next lecture. But for the moment being, let's turn to an alternative classical notation that we have for derivatives. It's the famous Leibniz notation. So to understand the Leibniz notation, which is pretty much the most classical notation for derivatives, let's just realize that what they did back then is they said, okay, here's x instead of just saying a, and the increment, instead of calling it h, we will call it x plus delta x. So that's the neighboring point. And then the output here is y, and the increment that you get in the y variable, you call it simply delta y. This letter is called delta. It's an uppercase letter of the Greek alphabet, and it happens to be the first letter of the word for difference in Greek, and that could explain why it was chosen this way. And so the difference quotient now, if you think about it, will become what? It's the difference between the y values, the rise, if you like, over the difference between the x values. And it's simply delta y over delta x. So now we take the limit as the increment tends to 0. That will be the derivative, of course, but I should not rush to call it that yet, and you will see why. Or to denote it by that, I can call it the derivative because it is the derivative. So here's the symbol that they chose back then. Okay, and it's a very questionable choice, but what they chose is to denote this limit by dy over dx. And the assumption here is that this is not a quotient. We should not think of it as a quotient, at least initially. It's just the limit of the difference quotient that we just created. So this is an alternative notation for derivatives. And it is called the Leibniz notation. So if you want to actually denote the derivative at a specific point, then you will just put dy over dx and x equals a, for example. And sometimes you can write things such as d over dx of x squared is equal to 2x. So by writing the symbol d over dx applied to a parenthesis or even one function, you express the fact that you're taking the derivative. It's like putting the prime. Now, at this point, I would like to say that every function that has a derivative at a given point is called differentiable at that point. So f is called differentiable at a if f prime of a exists. And of course, you might say, well, what can go wrong? And the limit that we create might not exist. And the easiest thing that can go wrong is that you can have a sharp corner. Take this, which is the graph of the absolute value, for example. And ask yourselves, if you were to take secants on the left, what would be their slope? And the answer is -1 because they all point downward at a 45-degree angle. And if you took secants on the right, what would be their slope? And their slope would be 1 now. So that tells you that if you were to take the one-sided limits for the limit that gives you the derivative, then the limit would be -1 on the left, +1 on the right. So the bottom line is that the limit doesn't exist. So in general, if you have a function that has certain sharp corners, you might expect that at those sharp corners, it's not differentiable. Now, can you imagine a function that has lots of these sharp corners, something like that, a sawtooth function? And you can make these vertices being closer and closer. But one of the things that people wondered was whether there are functions that are everywhere continuous, and nowhere differentiable. And I'm saying this because there's a very simple principle here that says that if f is differentiable at a, then at a, then f is continuous at a, meaning we shouldn't even consider the notion of differentiability. We shouldn't even try to take the derivative of a function at the point where the function is discontinuous. So let's talk about continuous functions. The function square root of x, the function absolute value of x that we were just looking at is a continuous function, and we saw that it fails to be different at one point. We could ask the question if there are functions that can be so extreme that they're everywhere continuous but nowhere differentiable. And that was a question that was very popular in the 19th century. The answer was found in the 19th century. People realized that there are functions that are everywhere continuous and nowhere differentiable. And in a very revolutionary result for the time, it turned out that in some sense, this is the rule and not the exception, even though in everyday life we find we have continuous functions that are pretty much everywhere differentiable, but theoretically that's not what happens. And there are some fascinating stories regarding this matter. In fact, there was a function, the famous Riemann function, that was proposed by Riemann to be, it's this function right here. So you take pretty much sine of x plus sine of 4x divided by 4, and then sine of 9x divided by 9, and then sine of 16x divided by 16. This function was proposed, and then you keep going. It's a whole story of what we mean by keep going, what we mean by an infinite sum here. But this function was proposed as a early example of a function which is everywhere continuous, nowhere differentiable. People were not able to prove in the 19th century that this was a successful example of such a function. And it was so interesting when in the 60s, a high school student, Joseph Gerver, was able to actually show that this function is differentiable at certain points. So f of x is differentiable at certain points. So it's not an example of such an extreme function. It was a marvelous result. If you would like me to write down an example of a function which is everywhere continuous, nowhere differentiable, then all I need to do is play the following game. So instead of, so I could start with sine x and then sine of 2x over 2 plus sine of 4x over 4 plus sine of 8x over 8. So you see, I was playing with the squares of the natural numbers before. Now I'm playing with the powers of 2. And it turns out that if I do this, actually the function that I get is everywhere continuous, nowhere differentiable. It's not an easy thing to show. I have to keep going here, but I hope that it's actually quite interesting to consider this much more advanced mathematical problem at this point. Okay, that's all I have for you today. Thanks for watching.